All right. So this time we are going to talk about a close relative of rotation. We are going to talk about oscillation, right? So in oscillation, typically we think about something that goes up and down, left and right, something that repeats over and over and over again, right? And so how are they related and how we can start thinking about this whole system? Obviously, we're not the first ones to start thinking about this, and this is where the whole trigonometry thing comes in, right? So one thing that you can start thinking about oscillating is a wave, right? The most common wave that we're probably most familiar with is a sine wave. So sine comes from the trigonometric function of sine. So if we go to a graphing calculator, hey, welcome to Desmos. So if I say that y is equal to sine of x, right? It's gonna draw a sine wave for me. So here it is, right? So it's something that goes up and down and up and down and up and down. And if we zoom in a little bit closer, you will notice that it fluctuates between -1 to 0 to +1 to 0 to -1. If you're very careful in observing, you will also notice that it crosses that 0 line at 3 point something. And if you're careful to guess, it will be 3.14. It will be the number pi. So that should give you a certain hint, right? Let's just kind of pin that idea there that it goes half of its oscillation in 1 pi of distance. Okay. And then the other half is going to go in another pi of its distance, right? So here's minus 3.14. So there's a whole oscillation between these two, right? So that's one idea. And the other idea is, so there's a complementary to the sine, and it's called cosine, right? So again, you might remember it, but if I say y is equal to cosine of x, you will find a complementary function that produces something very similar, but it just where it crosses those points is slightly different, right? So like 0, 0 on the sine is going to be actually 1, 0 on the cosine. So if you think about like just going into the positive numbers, you can say that our sine starts at 0 and our cosine starts at 1. And then it goes to 1, and then this one goes to 0. Okay? So we have those two complementary numbers, and they just go on and on and on. And if you just zoom out and see, it will go on forever like this. It doesn't matter if we're probing it at 50 or at 100 or at 1,000. It will always keep going in the same up and down, up and down, up and down, up and down, up and down. Okay, so that's oscillation for you. So how does it connect to trigonometry? So what is this whole thing? So I think I mentioned it before that everybody's biggest mistake is thinking that trigonometry is about triangles, where it really is about circles, right? And so when we talk about trigonometric functions, it's first and foremost something that has to do with circles. So you might have gotten an idea that it might have something to do with circles when we realize that our 1/2 of an oscillation takes up pi distance, right? And so the full oscillation will go in 2 pi. So 2 pi is the same as the number of radians in one circle circumference. So here is a different way you can think about those waves, right? Rather than thinking them as stretched out in time, we can all, or like stretched out in distance along the x-axis. We also can think about them looping back onto themselves, because we're going to go from 0 to 1 to -1 to 0, back to 1 to 0 to -1, and so on. And so you can literally loop it back. So at some point I was trying to kind of wrap my head around all of these concepts. I made this little trigonometry assistant, right? So this allows me to just kind of see what any and all of this means. So okay, so right now my angle commonly referred to as theta, right? This is the Greek letter theta. Angle is very close to zero. It's minus 0.1, but essentially zero. So my cosine is actually 1, and my sine is 0.03, whatever, essentially also 0, right? So when I start increasing the angle, right, here it goes increasing, my cosine is going to start moving, and my sine is going to start moving, right? So somewhere here where my theta is actually 60, right? So it's close to 60 degrees. My cosine is 0.5, right? So it's half the radius. And my sine is actually minus 0.86. So that same movement that we've observed is that sine goes from 0 towards minus something. And if I go the other way, obviously it's going to start decreasing, right? So sine is going to 0.2, almost 0.3, 0.4, 0.5, right? So sine is increasing. Here it is in bright green. And then cosine is decreasing at 0.6 or 0.76 right now. And then here it goes, here it goes, here it goes, right? So now my cosine is 0.5, my sine is 0.86, okay? So again, that same 60-degree angle, just in the other direction. All right, so what that should tell you is that cosine keeps moving along this axis, and then sine keeps moving along this axis, right? And this is how they're typically expressed in the trigonometry books, right? So you see I have a triangle written inside my circle, and the red line right here, that's the hypotenuse, right? And the angle here, right, that's the angle that I'm measuring. I have an adjacent line, which is like this brighter blue, and I have the opposite line, which is bright yellow, right? And so the bright yellow, I'm just simply projecting this bright yellow onto the y-axis, and that gives me my sine value. I could just as well measure my sine right here, but it's just a little bit more illustrative to take a look at it, how it's projected onto my y-axis. And then my adjacent side, that's just moving along the x-axis, right? So what that does is it allows me to kind of draw this triangle into my circle using the radius of the circle as the hypotenuse. So radius is hypotenuse, hypotenuse is radius. They're just different names to call the same exact thing, right? And the cosine is going to measure my x position, right? So that's going to be the x position of this point, of the point where my radius touches the circumference. This is the important point. So the x position of this point is going to be measured by the cosine, and the y position of this point is going to be measured by sine, right? And as I move this point along the circle, its cosine is going to move and its sine is going to move, right? So you can see how the yellow line gets shorter, the blue line gets longer, and then it goes the other way, right? And that just simply measures the point where my radius touches the circumference, right? This is the key point right here. All right, so there is a trigonometry primer here. It's in the P5 readthedocs.io. It's just something that I found. It's a reasonably good book. This tutorial is from a book called Processing, Creative Coding, and Computational Art by Ira Greenberg in 2007. I really like this article because I think it explains the concepts really well, right? So you have your hypotenuse, your opposite, and your adjacent. And so this is your angle, and this is the radius, and this is the hypotenuse, and this is that main point that we're measuring, right? And so like this is going to be the value of your cosine, and this is going to be the value of your sine, right? And so again, sine is just the opposite, and the cosine is the adjacent. So you can say that sine is the opposite over hypotenuse and cosine is the adjacent over hypotenuse. But remember how we talked about like thinking about our circle as a unit circle. So what that means is that I just assume that this hypotenuse, or the radius, is equal to 1 of something. Maybe it's 1 of meters, 1 of feet, 1 of miles. It doesn't matter. If it's 1, that simply means that the length of the opposite divided by 1 is just going to be the length of the opposite, right? That's all that is. So that's why it's so easy to assume that it's 1 of something. And then sine is just the length of the opposite. And then if hypotenuse is 1, again, adjacent divided by 1 is just adjacent. And then cosine is just equal to adjacent, right? So this article describes in detail how exactly it works, how it relates to your sine and cosine waves, and there's like a little bit of code written in original processing. So this requires Java. We'll have a completely separate conversation on what processing is. It's a counterpart of P5, but in a slightly different language, right? And so you can we'll come back to this, but you can also find similar code right here, right in the examples, P5.js examples, sine and cosine, right? So if you run it, it will give you this animated circles, and it show right, and you can easily see that this red point represents the sine and the yellow point represents the cosine, and they give you the angle. So they kind of did what I did, but instead of being interactive, it's animated, and you can look through the code and see how exactly they wrote it in order to produce this animation. So yeah, so where is it helpful, right? How can we actually make some reasonable use of it? So let's try and make something out of it, and we'll see how that can be applicable to us. But again, just to drive that point home, the fundamental idea is that if we want something to go back and forth or up and down and left and right just repeatedly over and over and over and over and over again, if you pay attention to this red point, it goes up and down and up and down and up and down over and over and over again. We can sort of like rely on sine and cosine to do this for us, right? So let's run things. So I'm going to try and create a sketch that would unify the two ideas that we've been talking about, the rotation and the oscillation. So I'm going to try to create a rotation that just kind of rotates back and forth rather than rotating over and over and over in the circle, right? So let's start with this. I am going to have a canvas. Let's make it relatively big, 800 by 800, right? And I'm going to separate it into rings, right? So just like we did an animation of rotating rectangles, I'm going to have rotating rings. So I'm going to do let number of rings be, well, let's do 10. We're going to have 10 rings, and each ring is going to be 20 pixels in sort of in thickness, right? So I'm going to say let stroke weight weight let it be 20 pixels, right? So okay, and then I'm gonna need a radius for every single ring, and I will but we can cross that bridge when we get there, right? So fundamentally, I have a sketch. It's 800 by 800, and I'm gonna set the color mode again to our very convenient HSB 2 pi for the hue, and then 1 and 1, right? 1 for saturation and 1 for brightness. And then yeah, so the radius is going to be the radius of the entire composition. So let's do this. Let radius is well, let's just define it after we figure out what the width is, right? So once we've created the canvas, we have the width of 800, and so now we can say that radius is equal to width times 0.1, right? Or to be a little bit more concise, 0.1, and that simply means that 1/10 of the width is going to be my starting radius for my composition. Okay, And yeah, we can start right here. So the background, let's make it dramatic. Let's make it black. Let's make it 0. And then no fill. We are not going to be using any fill because those are just going to be rings. They're going to be strokes around. And then stroke weight is going to be set to whatever my SDR weight, however it was declared on line 2, right? So here it's 20, so we're setting it to 20. Okay, so I need to create the rings first. Let's do the for loop, right? So if we have some repeated operation with small changes, we're always going to go into a for loop. So I'm going to do let I equal 0, right? For as long as I is less than the number of rings, right? We're going to do I++. I stands for iterator in this case, but it can stand for index or whatever it is that you want it to stand for. We just want a number, right? So first, I need to set the color of my ring, right? And we've already looked at how we can do this. So the color of the stroke is going to be color, right? So it's going to be some kind of a color. And I'm using a bit of a shorthand here. I think hopefully like these are the things that we've done before. So if it feels a little bit like what the hell's going on, go to some of the previous videos and recheck it, right? So we're declaring the color by taking the number 2 pi, and then dividing it by the number of rings. So that gives us how many sections we need to have. So 2 pi divided by 10 will be 0.628. So that's going to be the size of every section. And then it's going to be 0.628, 1.2, whatever. And so basically I need to multiply that by I. So I'm going to say I multiply that by that number. Right, so that's going to give me my hue and the saturation and the brightness. I'm not going to mess with it. I'm just going to have 0.9 and 0.9. Right, so I'm going to change the hue, but not the saturation, not the brightness for every one of the rings inside my for loop. Okay, cool, we've done that. And then remember, we're going to push and we're going to pop because we are going to be rotating something. Right? So if we want to rotate, let's do the rotation around the 0, point. Well, it's not like we have any choice, but it's always going to be around 0, point. Let's move that 0, point to the center of my sketch, right? And hopefully you remember how to do that. You translate to width divided by 2 and height divided by 2. So now we're at the center of the sketch, and you can start sort of drawing around that center, right? So I am going to draw a bunch of arcs, right? So an arc, if you look at the reference, and arc, it's one of the primitives, right? And the arc essentially is drawn the following way. So it's kind of like an incomplete incomplete rotation, an incomplete circle. So the first, let's go to the definition right away. So we're gonna have x and y is gonna be the center of the arc's ellipse, right? So around which point the arc is gonna be drawn. Okay, and then the next one is gonna be width and height of the ellipse. Okay, so all of my arcs are going to be drawn around the same 0, point. So I can say arc 0, 0, because if you remember, right, if I move my 0, point to the center, so now I'm going to start drawing all of my arcs around the center. Okay, and then I need to figure out the width of every single one of them and the height of every single one of them, right? Because it's going to be the same number. And so here's what I'm going to say. I'm going to have a radius, which is the initial point. Radius. Okay, and then if the width is basically radius times 2, the diameter, right? So radius times 2. Okay, so that's gonna give me the initial point, but then I need to kind of like keep going and going and going and adding and adding and adding so that they grow from the center outwards. So the first one is going to be the smallest, then it's going to be a little bigger, then it's going to be a little bit bigger, and then it's going to be a little bit bigger. So in order to do this, I need to, if you kind of got a gist of how, like the flavor of how these operations go, I need to somehow involve the position of the ring and its size, right? So somehow it's going to be letter I in there, right? And also I need to kind of like take into account the weight of the stroke. So each one of them is going to be sort of like determined by how thick it is, right? So we are going to do the following. We're going to do, so there's going to be, let's just put a space here. So I'm going to say stroke weight times I. Okay, so there's going to be that, right? And so I'm not gonna like do big jumps. I'm just gonna do increments. So I'm gonna take that amount and then add that to the radius, right? And then I can add that to the radius. And then the interesting thing is I need to multiply it by 2, and it has to do with the way the stroke is applied. So I can kind of like crudely draw this for you, right? So if this is the line, right? So my stroke is going to be applied on both sides of this line. So if I need to, and this is going to be the size of the stroke. So if I'm going to draw the next line for my arc, I also need to account for something like this, right? So I basically just need to double the size of my stroke. I hope it makes sense, but let's do it first without doubling it, and then we'll see what happens, right? So let's go back, and then it's going to be, since they're going to be circles, they're going to be the same. So let's just remember that we're going to have to double this number for the stroke at some point, right? And now let's draw them all like this. I'm gonna have them incomplete. So what I'm gonna do, if I'm gonna be drawing them around a circle, right? Let's move towards that circle now. So if I'm gonna be drawing them around the circle, I want to start somewhere. I want to start somewhere here, and I want to end somewhere. Well, actually, I'd rather do it backwards, where I start somewhere here and then go and end somewhere here, right? And if we're going to be counting from 0 point, so this is going to be my start, and then I'm going to have to do more than one whole rotation around the circle to my end, right? So if I wanted to encode an arc like this, right, I would have to say, so my starting point is always going to be, let's do quarter pi plus half pi, right? And we can be a little bit more concise about it. And so what that means in practical terms is that I went from here to here, that gave me half pi, and then I went a little bit more, right? Half of half, so quarter. And so that's where I got to half pi plus quarter pi, right? So, and then my end point is actually going to be 2 pi plus quarter pi. So 2 pi plus quarter pi, right? And so again, if we go back to our drawing, so the 0 point, the full rotation from the other side is going to be 2 pi, right? So if we go like this, that's 2 pi plus a quarter. That's how we got to that. All right, so let's run it like this and see what happens, and we're going to have to make some adjustments, okay? So error, great. Let's see. It's not SRT weight is not defined. That's because I misspelled it. Very common thing. This is why I copy and paste STR weight. And then something else. Oh God, it's a mess. So what I'm gonna do, I'm gonna take this value, copy, and then paste, and then paste, and what a mess. And something's not running. Let's find out what's wrong. All right, so what was wrong is that I went into an infinite loop. And I went into an infinite loop for one very simple reason. I never specified, or I incorrectly specified where I should stop, right? So I put a comma here instead of less than, right? It's just a misspelling, but it also like it crashed my browser and I had to like redo everything. So things like this happen, and I just had to be patient and wait for the browser to crash and stop and double check everything. And then I saw like this like propagating number of rings never stopping. I'm like, oh wait a second, I should take a look at where this is, right? But you know, mistakes like this happen. Just be patient with it. So all right, so we got to this point. Right, so here's what happens. See how they're like, you can see on the ends, they're like overlapping a little bit. So like one is, let me see if I can zoom in there maybe a little bit. No, actually no, but hopefully you can see that they're like overlapping. And that's because I need to double, remember I needed to double because otherwise my stroke kind of overlaps the previous stroke, right? So this is why I need to just multiply it by 2 in order for the strokes to get fully separated. And now they're like sitting right next to each other. Okay, and that basically has to do with how the stroke is calculated from the actual position of the ring. And then I also don't super like those like curly ends, and I want to change all of them. And so what I'm gonna do, there's a parameter called stroke cap, right? Stroke cap, and that determines what kind of cap you can have. And I'm just gonna set it to square. Square. Okay, so this is gonna give me a square cap. All right, so we drew our arcs. They're running. So now we need to rotate them. We need to rotate them in an oscillating manner. So they go like, but hopefully I'm gonna make it a little bit more interesting than that. I'm gonna have each and every one have a slightly different period, right? So if you remember how we did it with the rotating rectangles, we calculated the angle inside the loop, the angle of rotation, right? And so here's how we could potentially do it. So before I draw the arc, remember we have to rotate first and then draw the arc. I'm gonna say rotate, and then I am going to use the amount of time that has passed since the beginning of the sketch, right? So if you wanted to get something like this, let's go to reference. You can call up millis, right? So millis returns the number of milliseconds since the sketch has started running. So the reason why I'm doing this is I kind of want this like line to go on, to keep going and going and going and going. And this is what millis is going to give me. It's just going to keep incrementing by a small amount over and over and over and over again. And if you think about it, it's the number of milliseconds is going to start growing pretty long, because it's how many thousandths of a second. So I'm going to need to bring that milliseconds back to a small number. So I'm going to multiply it by, divided by 1,000 and multiplied by 0.001 to make it, again, like a small and slow number. And I'm going to use a trigonometric function. It almost doesn't matter whether it's a sine or cosine. I'm going to use a sine. And so I'm going to derive it from this millis, right? So let's just try sine of millis. Whoa, very fast, right? So what if we do now sine of millis times 0.001? Okay, so we're going to slow it down. All right, so now they're all going slower and nicer, and it just like that line keeps going up and down and up and down between -1 and 1 and -1 and 1 and -1 and 1. It keeps going and going, and that's actually the extent of rotation. It's 1 radian one way and 1 radian the other way, right? So +1 radian, -1 radian, +1 radian, -1 radian. But we can make it a little bit more interesting if we involve the number I, the position of the arc, into this calculation, right? So for example, and feel free to experiment with it yourself, what if I say that I'm going to multiply this by I times 0.5, right? Plus 1. And the reason why I'm doing plus 1 is if I'm starting my I at 0, 0 is not going to give me much. And so one of my circles, one of my arcs is going to be always static, which is not something that's particularly interesting. So I'm adding 1 to it, so I don't ever have to have them static, right? So now the amount of the angle of rotation also depends on the position of the arc in the sequence of arcs, right? Because number I is involved. And so now every single one of them is going to go differently. The ones on the outside are going to go much faster because as on the outside, the I is going to be like 9 or 10 or 8, right? So bigger number, faster oscillation. Closer to the center are going to be slower because we have either 1 or 2 or 3, so smaller numbers, smaller oscillation, right? Slower oscillation. Okay, so feel free to experiment with it. So what if you remove that plus 1, right? What happens, right? So that's the very first one remains static. That's what I was trying to avoid, right? That's what I achieved by adding that plus 1. But what if you change 0.5 to 0.05? The difference between them is going to become a lot smaller, and so they're going to go into much smaller differentiation. So that's the factor of differentiation between them, right? Feel free to experiment with this whole system and see if you can do something differently there, right? And if you can push it towards some other interesting results. But yeah, have fun with it.